So we fixed which did we fix, plus or minus? X. We fixed x plus to be equal to, now I had said zeta plus maybe sigma plus zeta minus sigma minus zeta plus.
How center of mass position?
Plus, yes. Yeah, but yeah, okay, let's keep that. Plus x. Okay, let's keep that. Yes, it's good. Okay, we fixed it to that. But of course, x plus, like anything else, is periodic as you move around sigma. Okay, so if we take, so let's see what this amounts to. This is equal to sigma plus minus into tau plus sigma plus sigma plus minus, minus sigma plus minus to sigma plus x0 plus. Okay, so now if sigma plus minus sigma plus minus was not 0, then x plus would not be periodic in sigma. Okay, so this was unnecessarily had unnecessary redundancy there. So we can more, if you say just x plus is equal to sigma plus, okay, let's stick to our notations, 2 sigma plus tau. Because sigma plus is sigma plus minus, we just call that sigma plus. Okay, and okay, fine, we can keep 0. Okay, so this was the gauge we used. We have these constraints. The constraints for t plus plus is equal to del plus x mu, del plus x mu is equal to 0. And we have t minus minus is equal to del minus x mu, del minus x mu, 0. Okay? And then what we did was to say, look, there are the xi's, x plus and x minus. Now what we did was to say that we could just solve for x minus in terms of x plus, using these constraint equations. This one allowed us to solve for the left moving part of x minus, the other one allowed us to solve for the right moving part of x minus. Okay? So we could completely solve for x minus, for more precisely, we could completely solve for all but the 0 moving of x minus, because everything here had derivatives. Okay? And we got a formula. Somebody read out the formula just for the factors. Okay, actually, so let's work it out, just to be totally safe. So, this one here, we wanted to know what it was in terms of x plus x minus. Okay? And that did we get just simply, was this just del plus x plus, del plus x minus? Was there a factor of 2? No factor of 2. Plus del plus xi, del plus xi equals 0. Sorry, there's a minus. Thank you. Okay. And then we use that to say that this is the same as, now we can substitute for what del plus of x plus is here. Okay, that's just zeta plus. Not 2 zeta plus, because you write this as tau plus sigma plus tau minus sigma. Okay, so this is minus of zeta plus times del plus, so let's take this on the outside, so del plus x minus is equal to del plus psi. Okay, now this completely solves, this is just some constant, some number. So this completely solves here for x minus, or at least all parts of x minus that have any dependence on sigma. Okay. Now, at the end of the last class, we also worked out the symplectic form. We worked out the symplectic form on the space of solutions. And you remember that what we got? So we had the action being 1 by 4 pi alpha prime, probably with the minus sign, and then xi dot minus x I prime xi dot the square minus xi prime dot the square without the minus sign. This was our action, and our symplectic form was 1 by 2 pi alpha prime delta xi dot wedge delta xi. This was the symplectic form on the I space. This is the I runs from 1 to d minus, or 1 to d minus 2. Okay? But before proceeding to complete the quantization in I space, I just wanted to remind, let's also work out what the symplectic form was in the plus minus directions. Okay? So in the plus minus directions, what do we have? We have 1 by 4 pi alpha prime. And then we had the action was with the minus x mu del alpha x mu del alpha x mu. Okay? So that was minus 1 by 4 pi alpha prime, so plus 1 by 4 pi alpha prime, x mu dot minus x mu prime, x mu prime. The minus disappearing because of the sign convention on the metric in the worldsheet, on the worldsheet of the string. Okay? And now we have to recast this object in terms of plus minuses. Okay? So that's the same as this. So that gives us is equal to minus 1 by 4 pi alpha prime x plus dot x minus dot. Okay. And then this comes with a minus. Oh no, I put the minus here. Okay, so fine. Yeah. So let me just look at the x plus x minus part. I've already worked out the xi dot. Okay? So x plus dot, x minus dot. What?
Minus
Minus dot. Minus dot. Minus x plus prime x minus dot. Okay. So the symplectic form here is what? So if you look at the symplectic form, here, what is the momentum conjugate to, let's say, x minus? It's x plus dot. And the momentum conjugate to x plus is x minus dot. Okay? So we get minus 1 by 4 pi alpha, right? 4 pi, we don't have that additional factor of 2 that we had here because there were 2 xi terms. Okay? Minus 1 by 4 pi. Then the rule is delta of momentum. So delta of x plus dot, so that's momentum conjugate to x minus, wedge delta of x minus, plus delta of x minus dot, that wedge delta of x plus. Okay, momentum conjugate to x plus and momentum conjugate. Okay. So, you see, we've got some sort of non-trivial symplectic form on the space of x pluses and x minuses. And now, this has the potential of significantly complicating the quantization. Because if we're going to substitute this pretty complicated expression into that symplectic form, and then work out the symplectic forms in terms of xi's, that runs the nature of giving us very complicated symplectic form. Okay? However, let's look at this expression for a minute. Remember that this expression has an integral over sigma. Remember also that x plus, okay, has only tau dependence. So it's independent of sigma. Now you take a quadratic expression, okay, with one term is independent of sigma and the other term is some arbitrary periodic function of sigma. It integrates to 0 unless you hit the 0 mode. The term independent of sigma and the other term. So suppose you've got an expression like AB. B sigma. These are both A and B are both periodic functions of sigma. Okay? A is just constant. So it's just integral B. That just picks out the zero mode of B. Okay? So what we're seeing is that the symplectic form here, vanishes except on the zero mode of X minus. Okay? Now, let's go back to our general strategy for quantization. You see, what we did was to get rid of a whole lot of degrees of freedom in X plus by solving, by just imposing, by using diffeomorphism. And then we use the constraint to eliminate a whole lot of other degrees of freedom. Those are X minus. And we're finding that we're in a very lucky situation. It's not lucky, engineering this way, but we're finding we're in a very good situation. Because most of the degrees of freedom that we eliminated by X plus vanish from the symplectic form. Okay? So those we can just throw away without significantly complicating ourselves for the remaining degrees of freedom. Okay? The one that does not vanish is the zero mode of X minus.
Is this some complicated manifestation of second class constraints on X minus?
Exactly. So what I'm saying, in other words, is that all of these constraints here are second class, except for the zero mode, which has non-trivial symplectic form with the degrees of freedom we're keeping. So that should not just be eliminated. Okay? So what we are seeing here is that in this case, what we should do is eliminate all of X plus, and that process does not complicate a symplectic form. It leaves the symplectic form of the degrees of freedom we're keeping with the simple guy, provided, and actually it would be wrong in other ways as well, but just, we should eliminate the zero mode. The term in X minus, such that del class of X minus is a constant. Okay? So we'll keep the term in X minus that has tau dependence. We'll keep the zero mode. Everything else we just eliminate, and we can, even for the process of quantization, just simply forget about X minus. Because they don't enter the solution, they don't enter the symplectic form. Okay? So great. Now we see that we're on the road to simple quantization. Because we've got simple solutions and a simple symplectic form. Right at the end, we have to deal with that one constraint, one first class constraint involving the zero mode of X minus. And we'll deal with that right at the end. And as we will see, that will have very interesting physics. Okay? But for now, let's forget about that term and proceed to our quantization. Is there any questions or comments? There's a certain style of physics in which you would justify everything we're doing with great elaborate procedure. You should always remember that this procedure was invented by someone. And, it's not God-given. It's more or less as good to proceed by nose than to quote some authority. More or less as good. So anyway, usually if you do something wrong, you'll find it. Okay, great. Yeah, so you can justify everything I've done with great application of Dirac's procedures. But I'm not going to bother to do that.
Exercises are also independent degrees.
Exercises are totally independent.
So you would want to develop the same...
but the exercise has no constraints. You've got exercise are just minimally coupled scalar fields in two dimensions. So for them, the quantization is trivial, simple. Okay? So the only complication was where there were constraints, which was all in this X plus X minus case. And we've seen that apart from the one thing involving the zero mode, we're instead of home. Okay? Great. So now let's proceed. So I'm clearing the set of the blackboard. Okay. So now it's easy to proceed. Let's proceed to the quantization of the exercise. We just started that at the end of the last class. Let's do that. That's very easy, but just once. So what we do is to take X plus and to expand it as x plus 0, sorry, not x plus xi 0 plus, let's say, zeta I, to be consistent, I'll put a 2 here. We'll interpret this anyway, so we'll have better. Zeta I times tau, because just like for x plus and x minus, I think we mentioned this last time, the term proportional sigma plus has to be equal to the term proportional sigma minus, because otherwise it would be periodic in sigma. Okay? So this is what I call the zero mode sector. We'll return to that right at the end. Now let's deal with the oscillators. The oscillators, we said the sum over n, I think I call them alpha n by n, e to the power I n tau plus sigma, plus sum over n alpha n bar by n e to the power I n tau sigma. We'd also mentioned last class that reality requires alpha n is equal to alpha minus n star. Okay? So this bar that we are talking about should not be confused with complex conjugation. Alpha n and alpha n bar are entirely independent degrees of freedom, both classically as well as well. Very particular classically. Alpha n and alpha n bar can be set to whatever you want. There's no connection between what's happening in the left moving side and the right moving. They're totally decoupled, including by complex conjugation.
The sum here runs over all values of n or just positives?
Now all values of n, and that's why we've got something involving a minus n. And we could group these together if you wanted to, but there's no reason. Okay? Now I'm going to work out this symplectic form on the space of alphas. The first thing to do, we'll deal with the zero modes right at the end. Let's do it first with the oscillators. The first thing to ask is, well, classically, the left and the right movers totally decoupled. Do they decouple quantum mechanically as well? It's a question of whether there's a non-trivial symplectic form between left and right movers. Okay? So let's work it out. Let's work out the symplectic form between left and right movers. Okay. So suppose in this expression I plugged in one guy here, left mover, and the other guy there, right mover. Okay? So, suppose the left mover is chosen to be alpha n. The first question is, what will the right mover be? Remember, we have to do an integral over sigma. So we only click if the sigma momenta are equal and opposite. So that means the right mover is alpha n. Because, if the left mover, I don't know which is right. If this guy is alpha n, this guy also has to be alpha n. Because there's a relative minus sign in the sigmas. Alright? When we do left mover with left mover, we'll only get non-zero click between alpha n and alpha minus n. Okay? But for left mover, right mover, we get click for alpha n, alpha bar n. Okay? And it's, okay. So let's work it out. So we just take the term here that, so we have, what do we have? We had 1 by 2 pi alpha prime delta xi with I dot wedge delta xi. So we get two terms involving alpha n and alpha n bar. When alpha n appears here and alpha n bar appears here, or the other way. Okay, so what are these two terms? Each of them takes a derivative. So each of them brings down a factor of I times n. Both I times n because we're using the same n. Okay, so we get 1 by 2 pi alpha prime in into delta alpha n wedge delta alpha n bar plus delta alpha n bar wedge delta alpha n, which is a simple way of saying, a complicated way of saying 0. Because wedge products are antisymmetric. Okay? I've missed out a factor of 2 pi that I get by integrating. It's okay if you miss out 2 pi. Is this clear? Was this too fast? Okay? Is it clear to everyone? It's an important point. Was it clear, Anandita? You're looking puzzled. No. Let's. Say this again. What are we doing? What we're doing is plugging in x here. The full expression for x, this whole expression. Plugging in the same expression here. And picking out the terms that have an alpha. We've seen that if we have an alpha n, we can only have an alpha n bar. So we're picking out the terms of an alpha n and an alpha n. What terms are these? Either we choose the alpha n in this expression and the alpha n bar in this expression, or the other way around. Okay? Let's evaluate one of them. I didn't miss out a factor n. I'm sorry. N squared, 1 by. Let's evaluate one of them. We get alpha n. Now we take the time derivative. So we get I n. We have a 1 by n. Okay? We get alpha n bar. No derivative, so that's just alpha n bar. Then the exponentials and sigma are cancelled. We're evaluating everything at t equals 0. So what's happening in time we don't care. And then we do this integral d sigma. That gives us factor 2 pi. So 2 pi divided by 2 pi alpha. That was this term. Okay? And then we get exactly the same term with the same prefactors. With alpha n bar, alpha n.
The 2 pi comes from where?
But the integral over sigma. You see, we're plugging this expression into this expression which has an integral over sigma. Okay? We make sure that the momenta are equal and opposite. So that's just a constant. So the integral of constant over sigma is 2 pi. Is this clear? But then we also have the other expression where we take the alpha n bar in this term and the alpha n in this term. They're completely symmetric. You get exactly all the same factors times this plus alpha n bar alpha n. But this is an antisymmetric range product. If both of them are equal to 0. Is this clear?
What is 0 mode?
The 0 mode we're dealing with right at the end. Okay, we'll put the 0 mode aside. You see that it doesn't mix with this because if you take one of these and another 0 mode, you'll get 0 by integration. So we can deal with the 0 mode separately. We'll deal with it right at the end. Let's worry about your status.
Sorry, but this one so you still have an integral in the last line. So there was just one integral over d sigma.
It's just one integral of d sigma because what do we, a symplectic form is on the space of configurations. It's like x wedge p. It's not an integral over time. It's just at one time. But the configuration space involves x's at all space. So the symplectic form is this over all space. So that integral is over. Here? No. That's also excellent. Other questions or comments? Okay? So great. We've seen that the left and the right movers decouple, not just in finding solutions, in solving constraints, but also in the symplectic form. So we can deal with them one at a time. Okay? So let's now deal with the, I don't know. I suppose this is what would be called a right mover.
So why does this mean the difference? What does this mean the left and right mover?
Because in symplectic form, there's no cross symplectic form. So when we promote quantum mechanics, there will be no non-trivial commutation relations between left and right movers. Left movers and right movers will commute. We can just separately quantize one. The Hilbert space we get will be a tensor product. Left movers and right movers. There's no non-trivial commutation. Is this clear?
No, I just see that you have just found out the omega from the momentum conjugate to xi and between xi.
No, I've converted that omega into the symplectic form between the alphas.
That's what I understand.
And we get no non-trivial symplectic form between left moving and right moving oscillators.
Okay.
So what we're going to do, it will become clear as we proceed. So we're going to use canonical quantization. Once we work out the symplectic form, we'll promote it to commutation relations using Dirac's procedure. And the fact that there's no non-trivial symplectic form between left and right movers will tell you that there's no non-trivial, that the oscillators of a theory commute with each other. mechanics in 2 dimensions, the Hilbert space of the first dimension is totally decoupled from the Hilbert space of the second dimension. It's a tensor product. It's like that. Okay? I was going to just quantum mechanics of particle moving. Non-relativistic quantum. Clear? Great. Fine. So now let us proceed. So we've got we get to deal with only left movers, only right movers. They be very similar to each other. This is the guy I think I should call a right mover. Because as tau increases, sigma must increase for the shape to stay constant. Okay, let's deal with the right movers. Oh, well, let's deal with the right. That's a plus. Plus is up. Let's deal with the right. Okay, so let's deal with the left movers. So now what do we have? Here what we have is the following. We have the symplectic form is what exactly? Now we just plug in left mover and left mover into the same formula. Okay? So we plug in left mover and left mover. Here we have an alpha n. There we must have an alpha minus n. But there are 2 ways it could happen. You can have an alpha minus n here and an alpha n. So what we get, let's do it carefully, so we get the up to pi's. Okay, first let's do it systematically. We have 1 over 2 pi alpha prime because that's what multiplies everything. We get 1 over 2 pi alpha prime because that's what multiplies everything. We get 2 pi because it's sigma integral. We get a 1 over n square because we put that in into our expansion. And now, if we take alpha n to be this guy, we get a factor of in. Alpha n wedge alpha minus. If we take alpha minus n to be this guy, we get a factor of minus in. Alpha minus n wedge alpha n. Now some of you are wondering, look, the slick argument of a symplectic form vanishing between left and right movers sounds very much like it will vanish between left and left movers also. But you see, no, that's not true because it is close to minus. Okay? So the symplectic form is now 2 pi cancel, nn, so we get pi by n, alpha n, wedge, alpha minus n with a factor of 2.
The alpha dash.
Dash?
Alpha prime. The coefficient. 1 by 2 pi alpha.
Alpha. Okay. Excellent. And now, we can just simply quantize. Okay? And now we can simply quantize because we know the rule. The rule is that if you've got this kind of symplectic form, okay, then the Poisson bracket is the inverse. So we have alpha minus n. Okay? Commutate, Poisson bracket, alpha n into, now we have to invert this, is equal to n alpha prime by 2i. Okay? Now, the rule for going from Poisson brackets to commutators is multiply by IH bar. Minus n also?
No, the minus n is 5. Why is it alpha prime and not alpha prime 5?
You're right about that. That's alpha. Oh, did I mess up both? So I got the 2 pi's also wrong? I got the 2 pi's also. Thank you. Fine. You're right about that. Let's get this straight. This should have been square. Right? Whole thing should have been square. No. That came with a symplectic form.
Yeah.
Okay, it's like
Momentum. Position was position.
Say alpha n seems to make dimensionless.
What have I made dimensionless?
Alpha n, so you probably have to extract some factors of alpha prime.
I will do that in just a minute. it's easier to first get the answer and then to know what factors. He said we've been crude in our expansion. We should have put in some factors. We'll do that. Okay. So first, let's work it out in without it. So we've got alpha. That's always happens to me. Looks like I've got a minus. Yeah, if we just stick to what we have here, alpha, we get alpha minus n, commutator alpha n.
There is probably an overall minus sign in the first equation itself because one factor will take 1 by n and the other is 1 upon minus n.
Very good. Thank you. Thank you very much. Thank you very much. So it's an overall minus n. Because the n square should have been minus n. Thank you. That was it. Thank you. Excellent. So this is minus. So this is minus. And now we're in business. So we get minus n alpha prime by 2. Okay? Or you can write this alpha minus n is equal to n alpha prime. Now this alpha prime by 2, as was anticipated, is an irritating factor to carry around. Okay? So it's easy to get rid of. We just write this as square root 2 by alpha prime alpha n, square root 2 by alpha prime alpha minus n is equal to 1, is equal to n. Right, just by multiplying through here. And then we realize that what we should have done is replace alpha n. So where we had alpha n, we should have replaced it, that variable by square root 2 by alpha. So that we would achieve if we multiply it by square root alpha prime by 2. Okay? So now what I'm going to do is to acausally change my definition. Okay? If I'd been systematic about it, I would have put tildes all through here, which you should do in your notes. Okay? All of these were tildes, and now the actual expansion is square root alpha prime by 2, square root alpha prime by 2. Okay? With no tildes. So we've magically removed the tildes from the board. And then this. So if I have been foresighted enough, this is how I would have defined it at the beginning. But of course, who can remember factors square root alpha prime by 2? So you have to work it out to get it right. Okay? And so the final result with this new untilded definition is alpha minus n, sorry, alpha n, alpha minus n is equal to n. Okay, is this okay? Was it too confusing? Is there anything confusing about it?
How do which thing to put first and second, how do you decide?
Which thing to put? We have it in the symplectic form. This came with the minus sign. If I switch this, I would have got a plus sign. So now all I have to do is, this is some matrix with lower indices, all I have to do is invert it. Okay? Because I inverted it, I switched direction. Okay? And then I kept these.
With whatever sign?
With whatever sign it was. All you're doing is inverting the root cross matrix. And he said, just invert the matrix. Is this clear?
It's not different, but I think in that mode expansion, the summation over n should be multiplied with a factor of I. Otherwise, there's reality condition.
Very good. Actually, I was going to yes. Thank you. Now, the next thing to note, exactly as was said here, is that you want to multiply everything with a factor of I. Why is that? The reason is the Same reason pointed out earlier. And that is the actual factor of n here. So these things look, with our definitions, because of the reality condition, alpha n and alpha minus n, okay? Alpha n and alpha minus n would not be complex conjugates with each other, but negative complex conjugates because of this factor of n. Okay? So, if we put a factor of I, it will change nothing in the combination relations because it will change nothing in combination relations. I messed up the sign again. Just oh god, I messed up my signs. You're right, we need this for reality. Absolutely right. Let's put it here. And with this, we should have got this. But you say, how are we going to minus? Oh God. So where are we?
Why were you getting that minus sign?
What? This one here?
Because of that item only, right?
Well, yeah, so the 2 points that were pointed out cancel each other out. So now we get a plus, and we still have the wrong sign.
Actually, there was no sign. So if the extra minus sign you put at minus 1 by 2 by alpha prime on the right side, that would appear now. So that will give you an extra, because it's not n into n minus n, it's minus in into in, which is a plus n squared.
So that we're just going to plus, right?
Yes. Yeah.
Okay.
And then
That will change the sign.
That gives us the wrong sign, unfortunately. We just follow that through. Have I made a mistake in inverting? Well?
The alphas will also get an I, right? So if there's a plus on this side, it becomes a minus again.
No, same thing. Just like alpha gave us we put the array or now we're getting an additional.
Okay. Now we have two options. We can either spend the next 5 minutes tracking down the minus sign, or I can leave it to you as an exercise. Okay. We should very carefully check that we started with the correct symplectic form to start with the right signs, and I'll go through it correctly. Okay, people, I'm sorry about this, but I'm going to leave this as an exercise. Okay, because if there was a textbook that did it my way, I would refer you to it, but I don't think we know of one. Is it okay? Is it okay? It's not worth the 5 or 10 minutes we're spending on time on this. I'm sorry, I should have just done my homework. I should have worked this out at home. That's boring. Okay.
Just one. In going to the symplectic form, which is of the form alpha n wedge alpha minus n, you go to Poisson bracket and invert the ordering of alpha.
I did that because I thought that's what one should do, but let me check. Okay. What we have is the symplectic omega with lower indices.
Yes.
Okay, omega with lower indices was, let's say, 1 minus 1 0 0 times some stuff, some zeta. Now, what's the inverse of this matrix? The inverse of this matrix is minus 1 1 0 0 times 1 over zeta. Okay, so that should be omega with upper indices. To incorporate the minus 1 1, I switched order, and then I just verify. Okay, people, I'm sorry. Let's not get into this. Okay, what I can do is I can promise to work it out at home carefully and give you where I made my sign mistake by next class. Okay, sorry, it's not worth spending the time. When you do it right, this is what you should do. Except, just one minute. Just one. Oh, except maybe it's right. Just that is this might be it. I'm sorry. You know what I should have done? This is what I should have done. Because I want alphas with class n to be annihilation operators. Okay? Annihilation operators, just let's check. Annihilation operators usually appear with e to the power minus. This is important, so we'll just get that straight. Just a moment. Let's figure that out. You know, if you've got a state in a quantum field, firstly, Schrodinger's equation has states that go like e to the power minus I, e to the power minus I. Now, a state in a quantum field theory, a Schrodinger equation corresponding to a state in a quantum field theory is psi, the state, times the field on the vacuum. On the vacuum. That's where the Schrodinger state is. So suppose I take the state E dagger. That should come with positive energy. So e to the power minus n. And that will only work if this A here is e to the power minus n. So that's correct. Okay, so that was my mistake. It's a bad mistake. I'm sorry about that. And now we're on to this, right?
Here actually then if you change all the n's by minus n, then really nothing changes.
No, but it switches whether you're doing n or minus n. It just gives you an overall. See, it's basically a redefinition of alpha n to alpha minus n. Okay? So what you get here is alpha. We would have got that we observed correctly. We would have got this, then we switch it. We get the extra things. Okay. Now we got the signs, right? I'm sorry. So we did the algebra very carefully. We just did the conceptual part wrong. Okay? Now we fix that. Now we've got everything working hunky-dory. Okay? So this is our final expansion. And we're out there. Okay? And with that expansion we get this. Okay, I'm sorry about the sloppiness. If this has confused anyone, we'll take the 2 minutes to clear it up. Is it clear? You say in the expansion of harmonic oscillator, if you open your favorite quantum mechanics book, you'll find that the annihilation operator appears with the power minus IT. Okay, that's what we got. And I wanted my labeling to be such that positive n is annihilation operator. That's the standard labeling. It's just a convention issue. Okay. Excellent. Fine. So now we've got this beautiful expansion for the XI fields. And we'll etch it in stone. And we've got these beautiful commutation relations, which are alpha n, alpha minus n is equal to n. Okay? Now, let's compare the commutation relation for harmonic oscillators. You know that A dagger is equal to 1. We're setting H bar is equal to 2. 2 Okay. So we know that A dagger is 1. So these alphas are like square root n times destruction or square root n times creation. Okay, so what we've got is a harmonic oscillator Hilbert space for each n, where alpha n is equal to square root n times the corresponding A, and alpha minus n is equal to square root n times the corresponding n dagger. It works very nicely because alpha n and alpha minus n are complex combinations, which are daggers of each other, 1 to 1. Okay? So now what is our Hilbert space? Apart from 0 moles, which we get to very soon. Apart from 0 moles, what is our Hilbert space? For each n, there are d minus 2 into 2 harmonic oscillators. For every integer. Okay? D minus 2 because there are d minus 2 i's, into 2 because they're both left-movers and right-movers. Okay? And that's our Hilbert space, plus the Hilbert space of 0 moles, which we'll come to in just a minute. Okay? So we want to specify a state in the Hilbert space of the string. We have to specify a state by specifying the state in the Hilbert space of d minus 2 into 2 into infinity harmonic oscillators. And the infinity is 1, 2, 3, 4. But of course, as always in physics, the infinity will be graded by energy. So most of these oscillators will never be excited because exciting them costs a lot of energy. So you know this infinity in the Hilbert space, but not in dynamics. Okay. Fine. Plus whatever we get from zeros. We'll come to that in just a minute. Okay? Fine. So exactly the same analysis will go through for the right movers. Okay? Go through with no modification for the right movers, and I will not try to outline that. Wonderful. Okay. Now let's turn to the zero modes. Okay. Now let's turn to the zero modes. So let's first turn to the XI zero modes. Actually, it's the same. Anyway, but let's first turn to the XI zero. So the XI zero modes are very simple. What's the action? The action was 1 over 4 pi alpha prime with a minus xi, okay, with a plus xi dot squared minus xi prime. D sigma d tau. Okay, now let's work out this action restricted just to zero modes. That's extremely simple because firstly xi prime, this xi prime stuff, this doesn't contribute. Okay? So, this doesn't contribute, we just get xi dot. So, zero modes behave just like particles. Because there's no dependence of sigma, it's just dependence of tau. So, we just get xi dot, but we get the extra factor of 2 pi because we have to do the integral over the worksheet of the string, the sigma integral. So, things become 1 by 2 alpha prime xi dot squared. Now, we had some convention. It's not ugly too, but anyway. Let's just call it xi dot. Just the zero mode time derivative. Okay. Now, how do we quantize this? What Hilbert space do we get by quantizing this part? This we're very familiar with. This is exactly the action of non-relativistic quantum mechanics. Just exactly the action of non-relativistic quantum mechanics, but with the role of mass replaced by 1 by alpha. Okay? So the canonical quantization here will be just very familiar. We don't even need to do the symplectic blah blah blah. The momentum pi conjugate to zero mode is xi dot by alpha prime. The momentum is xi dot by alpha prime, and the canonical commutation relations are xi0 and momentum pi Pj is equal to delta H. Okay? Great. Because we now know.
Alpha prime is here.
Sorry?
Alpha prime is a numerator.
Alpha prime. No. Because we're just taking derivative of this. Okay? And now, since we know a good name for xi dot, a good name in the canonical formulation, xi dot is simply alpha prime times p. We can replace these ugly zetas by physical names. Okay? So we replace our zero mode sector expansion by xi is equal to x0i plus xi dot was alpha prime. Yeah, so alpha prime pi. Okay, just a name for this coordinate, but by the way, I'll give it the name that will make the canonical computation relation. With this name, okay, xi0 and pi have the standard computation relations. Sorry, after quantization. Is this clear? Okay. So now what is our Hilbert space? Okay, now as far as zero modes are concerned, okay, the x plus and x minus directions behave identically because we've not allowed ourselves to do anything in the zero mode sector. Okay, so what we get, so what at this stage state is our Hilbert space. Our Hilbert space is the Hilbert space of 24, d minus 2 into 2, d minus 2 into 2 into infinity oscillators, plus the Hilbert space of square integrable wave functions, square integrable functions of d variables. Because because the x plus and x minus directions behave just like the x directions as far as 0. Okay? Have we finished? Good. Have x plus x minus both behave identically as far as 0 is concerned, except we're not quite finished. Because there's one bit of the constraint that we didn't impose by eliminating degrees of freedom. That was the constraint, and that's what we were referring to, which determined the 0 mode of x minus. That was the constraint which determined the 0 mode of x minus in terms of oscillators of the xi's and other things. We decided we'll impose that constraint as a first class constraint. So we'll impose it as a condition on states. Okay, we'll impose it as a condition on states that our states have to obey. So we have to just do that imposition and then wait. So let's do that. Now let's remember what the constraint was. The constraint was minus x minus del plus x plus del plus x minus plus del plus xi del plus xi is equal to 0. Only the 0 mode part of this constraint remained. Okay? Now we have to keep our wits about us to get the signs right. We had gauge fixed x plus to have only to be, and once again, we gauge fixed x plus to be x plus is equal to, what is it, square root alpha prime times p plus tau. And therefore, del plus of x plus was square root alpha prime p plus by 2. Okay, we called it some zeta plus, but we're replacing that by the physical name. It's a change of notation. Because now we understand what the physical content of the notation is. Okay? So del plus of x plus was minus
square root, yeah, no square root.
No square root. Thank you. Minus alpha prime p plus by 2. By 2 because we want to write this in terms of x plus and x minus. So we write that as tau plus sigma plus tau minus sigma by 2. In order to be able to get del plus. Okay? Then we get a similar alpha prime by 2 p minus. Okay? And then what do we get from these guys? Okay? What do we get from these guys? Here what we get, we just remember it's only the 0 mode part. So here what we get will be plus alpha prime by 2 the whole thing squared pi squared from 0 mode times 0 mode plus whatever we get from oscillator times oscillator. Okay? So oscillator times oscillator, now we have to get signs right. Okay. So we will get this I and the n and minus n will give us no sign. So plus alpha prime by 2 because of this stuff. Okay, alpha minus n, alpha n. Do not be careful about order, though it will eventually be very important. At the moment, we'll just sum over. Okay, sum over all that. Okay, is this clear? Okay, is equal to 0. All I've done is plug in this expansion into here, and the zero mode expansion into here. So only zero mode.
So if you want to carry over order, it should be a factor of 2.
Well, I'm summing over all n going from minus infinity to infinity.
So both ways you get minus n plus n minus n.
Yeah, exactly.
So you get alpha prime alpha prime by 2.
Yeah, so if you convert this into a sum from 1 to infinity, I get rid of it. The term alpha minus 1, alpha 1 appears 2 times in my sum.
Yeah.
So if I process that sum to, I just don't want to do it because this is the natural ordering that comes about.
I think if you don't care about anything else, just alpha prime by 2 you put.
I agree that this can be, so this is equal to minus infinity to infinity, not including 0. And this, I agree, can be written as alpha prime. N is equal to 1 to infinity if you don't care about ordering. Alpha minus n, alpha. Is that what you say?
No. I'm saying that in the top only you need a factor of 2.
Oh, I need a factor of 2 in the top.
Because the Doppler, there's xi, right? It will come from both ways.
Xi.
Doppler xi. So you can get minus n or n minus n.
Minus n? Oh, you're probably right. Let me put that. Yes, but that's accounted for here, right? So suppose I take minus 1, 1. That occurs when this is n is equal to 1 and n is equal to 1. Suppose I want 1 minus 1. That comes when n is equal to minus 1. Yeah. So in the summation, if I write this as summation from minus infinity into infinity, then I've just accounted for it. You see, I've just plugged in and clicked.
This is minus infinity, right?
This is minus infinity.
That's 4 times, not twice.
I don't know, maybe I'm doing this wrong, but let me just work it out. So we get n is equal to minus infinity to infinity, always excluding 0. Alpha n times m is equal to minus infinity to infinity alpha m. Right? That's what we start with. Okay? Now, because we want 0 mode, m has to be minus n. So I'll just replace this by there's a delta m minus n, so this is simply n is equal to minus infinity to infinity alpha n alpha minus. No additional factor. Okay. Excellent. Excellent. We check if we've got a factors of 2 right, if we get the tachyon mass right. Because we never get it right first shot. Anyone who gets that calculation right first shot is clearly cheating. Okay. Okay, great. So this was our equation. Now what is the logical structure of this equation?
I just want to know, why is it only the 0 mode contributing to the del plus x minus e? You know x minus as a product of the...
You have everything, but x plus del will be 0.
Yes.
So 0 mode times something can be 0 mode only if that something is a 0. Momenta. Okay, so 0 momentum times unknown momentum is equal to 0 only if the unknown momentum is 0. Okay. Simpler way of saying this is just a constant. So this guy just has the Fourier mode, and you're picking out the 0 mode parts. So you only pick out the constant. Is this clear? Okay. Other questions, comments? Fine. So now what is the logical structure of this equation? This equation has to be imposed as an equation on Hilbert space. Now first let's simplify it by getting rid of some, let's write it in the way the product wanted with an alpha prime and sum over n. So we get the following equation. We get the equation that p plus p minus pi square is equal to 4 n is equal to 1 to infinity alpha minus n alpha i. Up to order.
P plus T minus looks bad.
What?
P plus T minus looks bad. Right?
It should be the other way around.
No, there should be a factor of. Oh, there was no square root to it.
Yeah. No, this was exactly the combination.
Okay.
This was exactly the Lorentz combination. That's where it came from. Okay? Now, this is simply P0 squared minus P all space squared. Okay? Oh, maybe Lorentz notation. Minus P mu P. Okay? Is equal to 4 by alpha prime times. Now we're going to understand this is an infinite sum and there's something to worry about in the ordering. We're going to come back to that in just a minute. Okay? But before that, I want you to understand what the logical structure is. You see, what is the logical structure of these P's on Hilbert space? They're derivative operators. Because our Hilbert space is wave functions of x mu's. The zero mode part of the Hilbert space was wave functions of x mu's. And P was implemented by I times derivative. Okay? So there is where you come d mu d mu. Okay? On wave function is equal to 4 by alpha prime blah 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 on psi. Now you see what's happening. What we get here depends on which state we are in our harmonic oscillator. But we can always choose a basis. In fact, this is just the occupation number basis. Okay? In which we get definite quantum numbers for this operation. In such a basis, what does this equation become? Okay? On the right hand side, okay? On the right hand, simple Fourier offering. Oh, by the way, the way of working in which you take the world-shape metric and use it as dynamical degree of freedom is called the Polyakov action. Polyakov. The way without was called the Nambu-Goto action. Not sure if okay. So, as we've emphasized in the previous classes, the Nambu-Goto method and the Polyakov method are equivalent only when we take great trouble to preserve wild invariance of the Polyakov formality. Now, wild invariance in particular implies invariance under scale invariance, under scale transformations. Because it's a simple scale transformation, simple rescaling of all coordinates is a wild transformation. And because it can be more precisely, a simple rescaling of all coordinates can be undone by wild transformation, and therefore it's symmetric. So scaling is a symmetry of our theory. Any theory that has both diffeomorphism as a wild symmetry, the invariance under what's called conformal transformations. We'll get back to that in a minute. In maybe the next lecture, but in particular there is invariance under scale transformation. No theory with an inherent length scale in it can be scale invariant. Okay? Now, if you take a theory and compactify it on a manifold of a certain length, then that puts a length scale in the problem without necessarily having it in the theory. But if you compactify it on length infinity, then there's no length scale. If there's no length scale in the theory, there's no length scale in the problem. So when we take the theory on flat space, infinitely compactified, we better get zero energy. Because otherwise there's a length scale in our theory. And we'll come back to Hiccups in a bad way as we proceed. So this is our physical prescription. We're going to add counterterms to our theory to make sure that the vacuum energy of the theory on R is zero. Because of the principles of quantum field theory, that we're only allowed to add local counterterms, and the counterterm doesn't care about where you put the theory, that will then unambiguously determine for us the vacuum energy when we take the theory not on length R, but on a circle of length N. Of circumference N, 2 by N. Okay? And that will not turn out to be zero. There's a name for this effect. That if you take electromagnetism and you put it on a circle of length 2 by R, you don't get zero vacuum energy. Does anyone know the name for this effect? Yes, I heard it whispered, but nobody said it. Casimir effect. It's more commonly said about two plates. Similar. Okay? So, what we're going to see is that when we demand that the vacuum energy, the energy of the vacuum, non-compact space is 0, the Casimir effect will unambiguously tell us what the energy is in a circle. We're interested in circles of length pi. So we get an unambiguous answer to this. So quantum field theory will give us an unambiguous way to assign a number to 1 plus 2 plus 3 plus 4. And it will turn out that the right answer for 1 plus 2 plus 3 plus 4 is minus 1 by 12. Okay? Now, in the rest of this lecture, let us try to understand how that works. Is the basic idea, philosophy clear? Okay? This is just 1 second. There are many parts of string theory that are discussed in a sort of voodoo way by many string theory textbooks. Many string theory textbooks at this point will say, now we will zeta function regulate the sum. 1 plus 2 plus 3 plus 4. And that's great if you're a mathematician interested in zeta function regularization. But we're not those. We're physicists. We want to do the right thing for the motion of the string. And we want to know not how you can get some number, but why it's physically correct. And this is the reason. This is the underlying reason. Please go.
So, you add this counter term to the Navier action.
You can add it to whatever I'm going to add it to the Polyakov action because we want the Polyakov action to quantum mechanically be equivalent to the Navier action.
Okay.
And that will demand that the Polyakov action does not have a length scale. Okay? So we're getting a creeping length scale from quantization. Okay, I'm going to remove that length scale from the Polyakov action.
The second is that when you say that compactification on R, what you
It's not compact. It's just putting the theory on R. Uncompactified.
And so you don't have any length scale or something like that.
Exactly. That's the point. So when you have no length scale, you must get vacuum energy 0.
So isn't it similar to like putting it on zeta function regulation?
There you go. It's similar, no doubt, and you get the same answer. And there are very good reasons that you do.
That's an infinitely.
No, but two different people who choose to regulate the theory in different ways might get different answers. You use zeta function regularizers, someone might do some other favorite thing. There is no unambiguous way of getting a finite number out of an infinite sum without specifying a principle. And the principle here is that we only add local counter terms. The local counter term is chosen to give you 0 energy in flat space. Okay? Once you've stated this principle, you can implement that principle in any number of ways. But this is the principle, and it's very important to keep in mind. Okay? Why is the other thing that is important to remember is you cannot, because you only allowed to add local counter terms. That's a property of the theory. There's no ambiguity in what the energy is as a function of L. Because once you've chosen your counter term, you've chosen it. Over, into this. Okay? Then the answer is what comes out. So quantum field theory is not the kind of thing which allows you to get any answer you want. There are counter terms, but still it's predictive. Because you can only add few counter terms in a very specified way and perform an infinite number of measurements. For instance, in this case, you can add one counter term and compute the energy as a function of length for all lengths. Quantum field theory gives you freedom in how to add the counter term. That freedom I've just fixed by my principle. But in general quantum field theory, you wouldn't have that principle. It gives you freedom of one. But it gives you an infinite number of predictions with that one term. You see? So it's not an anything goes subject. It's a subject with great predictive power. Okay? Great. Yeah. So, in the end, it will turn out to be zeta function regularization, so I will not argue with you. Yeah.
In usual quantum field theory textbooks, there is another way that we regulate this vacuum energy. We just say that.
No.
Yeah, we have this prescription of saying that we'll always normal order them, and we don't need to use a counter term there.
Yeah, but this is fine if you're doing one particular space. Let's say you're look at the theory on R2. Normal ordering is equivalent to cutting off and adding some counter term. Okay? But what you want to make sure is that when you study the theory on, let's say, an S1 of length L, You're not changing the counter term as you change L. Because if you do that, then you're studying not the same theory compactified on us, but different theories compactified on different methods. And if you just naively know about them, that's what you will end up. Okay? So that is a dangerous game to play. Basically, normal ordering is a useful thing when studying field theories. Okay? But you have to be aware of its limitations. The fundamental principle is regulate, add counter term, make sure it's local. That's the fundamental principle of quantum field theory. Fundamental. This is what we're supposed to do. Then there are many ways of implementing it. You know. Then you can go away to your office and do what you want. But you must be sure you're not violating, that you're doing what you're supposed to do. How you implement it. Okay? Yeah. Is this clear? Okay, please go.
So you're saying like K is some function of K mu for both for some circle and for line.
What is K mu?
K of mu is the cutoff. Right. And
yes.
So suppose you had an interaction theory.
Yes.
I could look at calculate the counter terms by Feynman diagrams.
Yes.
So is it obvious that I would get the same answer on
No, but you cannot quite calculate the counter term because there's always a finite continuity. Counter terms by the calculation procedure are chosen to remove divergences. But then you can always add a little bit extra, just a finite renormalization.
But it's fixed by the fact that you get
it's fixed by renormalization constants.
Yeah.
Okay? So, my renormalization constant in this context is basically the statement that I have zero vacuum energy at infinity. That fixes the ambiguous part of the counter. Right? So, what Ronak is saying is the following. In ordinary quantum field theory, let's say we do 5 and 4 theory. We can compute the counter term we need to add for the 5 and 4 coupling. How the 5 and 4 coupling will vary as a function of scale. We can compute that by computing the divergences in finite diagrams. That's true. But that can never give us a finite part. The finite part is then determined by one renormalization condition. For instance, a scattering at some energy. Okay? That's the structure of quantum field theory. You need to do a few experiments to fix your theory completely. Once you've done those experiments, it's fixed. So this is that experiment that we're doing. Fix the vacuum energy at infinity and unambiguously determines them. But now that becomes a counter term for all L. That's the crucial point. Okay, come. So let us proceed and complete this. I'll take 10 minutes extra today, okay? Just to get to the punchline of this. Okay, great. So now let us proceed and do this. So, what did we have? We had del alpha xi, del alpha xi. Maybe let's write it in terms of dot, right? Xi dot squared minus xi prime squared. 1 by 4 pi alpha prime. We have this theory, and what I'm saying is that we need to add some number here. Okay? We need to add some number here. Or let's call the number A. Just some constant. Okay? What I'm saying is that we need to add some number here, just some constant. And that number there, up to sign, is simply the vacuum energy of the theory due to the counter. Okay? Up to sign and a factor of 2 pi. If you integrate, it's just the vacuum energy of the theory due to the counter term. Okay? However, if you're on a circle of length L, the vacuum energy of the theory, I won't bother to get the signs right, will just be 2 pi L times 4 pi alpha prime times A. So if we add a counter term, it can remove a part of the vacuum energy proportional to L. do is to work out what we get. Okay, what do we get for the vacuum energy of our theory once we regulate, cut off, and work as a function of a circle size. Okay, so we're interested in circle size 2 pi, but in order to understand how things work, we'll generalize this to an arbitrary circle, a circle of circumference 2 pi. Okay, so what's our vacuum energy? We had said that it was 1 plus 2 plus 3 plus 4, but that's what it is on a circle of length 2 pi, of circumference 2 pi. Suppose we had circumference 2 pi I, how would this be modified? One by K. Omega is K, right? It's mass scalar field. It's not you're using. Okay, yeah. It's an L squared over not L. Yeah. Okay. Yeah. So it would be 1 by L plus 2 by L plus 3 by L. Okay? So this quantity here is simply half of d minus 2 times sum over n by L. That's clear? It clearly introduces to this quantity when n is 1. Now, how do we regulate this? What we do is to put one way of regulating is to multiply this by a function that vanishes at k equals infinity. Okay? But it's very important that we regulate not in a circle specific way, but in an invariant way. So we will regulate on absolute distances or absolute momentum. Okay? So suppose we multiply this by some g of n by L lambda. So this is equal to g of mod k by L. K is the momentum in the mode. Okay? We want to use the same regulator and same cutoff for circles of different sizes. And the way to do that is to tune your regulator to absolute distances, not think in terms of n. Had you done what I'm doing here and said this was g of n, this would be wrong. That would be using a different cutoff, different regulator scheme for different circles. Okay? Where g is a function such that g of 0 is 1, and then it smoothly decays away as you go off. Everything smooth. You see that this is a regulator because only those momenta that are small compared to lambda will contribute. Okay? Those momenta that are large compared to lambda will be cut off. That's what we want from a regulation scheme. The length scale of this regulation scheme is lambda. The energy scale of the regulation scheme is lambda. Lambda is going to be taken to be a very large number. Is this clear? This is a good way. This is one way of regulating it. Another way is zeta function regularization. Okay. Yes, but this is physical. Good. Now, what I want to do is to take this sum and perform the sum. Okay? And I want to make sure that it's the answer I get in the end. It doesn't depend on what regulator function I use. I just keep it. Check. G is some function that does this. No details. And then, how do I evaluate this? Well, there's this wonderful thing called the Euler-Maclaurin formula. Some Maclaurin formula. Okay. Okay. Which allows you to evaluate sums in terms of integers. Okay. And the formula is that if if you've got a function and you take g of 0 by 2 plus g of 1 plus g of 2 plus so on, this is equal to integral 0 to infinity of g of x plus g prime of 0 by 12. And then there are further correction terms proportional to g triple prime, g fifth prime, and so on. The numbers that appear in this expansion have some name. I have Bernoulli, maybe the Bernoulli. This is Bernoulli. Some well-studied numbers. All we will care about is the first term. It's the only thing that will matter to us. And this actually is minus. I think this is probably the statement that B1 is minus 1 by 2. It's the first one. Okay. I'm not going to try to derive this formula for you people. I'll ask you to look it up in the right place. But the basic idea is that sum is almost an integral. There are corrections. And this is a beautiful, precise version of that statement. Okay? Fine. Now what we're going to do is to use this lovely formula, okay, to evaluate this object. Okay? So I shouldn't have used, let me call this H. Okay, so because I've got a G there. So our H of x is equal to x by L G of x by L.
You have to assume that this g prime of 0 and minus g prime of infinity by 12 means the first connection is of that form. Then there will be residues in this Euler-Maclaurin.
Minus g prime and infinity? Yeah, I'm using this. Sorry, is that the question? Is what happens at infinity?
Infinity, g prime.
No, I'm assuming that this function, this integral that we're looking at, is well behaved. So g goes to 0 sufficiently rapidly.
And the derivative of the g?
Everything goes to 0 sufficiently rapidly at infinity. That's clearly true of our situation because we took this derivative function. Okay? Usually integrals to infinity are only well defined if things are far. Okay. So now what we're going to do is the following. We've got this situation here. So we've got our okay. This is our thing. Now, with this thing, the left-hand side of this Euler-Maclaurin thing is exactly what we need here. So what we want is d minus 2 by 2 times L. You might ask, what about this factor of 2? We didn't have this half here. But that's fine because our h of 0 is 0. Okay? So now what we're going to do is evaluate LHS by evaluating the RHS. Okay? So the RHS is 0 to infinity x by L g of x by L lambda dx. Okay? And now what we'll do is a change of variables. We change variables to y is equal to x by L lambda. When we do that, we get an extra factor of L lambda. Exactly. We will write x is equal to L lambda, and so we will get a factor of L lambda squared, as Shubhati correctly pointed out, y g of y d1, 0 to infinity. Now this g is chosen for some function that looks like this. So y g of y dy is some number of order 1. What number depends on what g we've chosen. We cannot say the general grounds. But so what we get here is this L lambda squared times the number of order. Okay? Important point is that this is ambiguous. what we get depends on what the precise nature of the cutoff we chose. But the ambiguity is always a term multiplied by L. And so it's precisely the kind of thing that can be cancelled by a local counter. Okay. Now let's evaluate the next term. When we evaluate the next term, we get what? We get that we have to take the first derivative of this h guy. And we can either hit the derivative could either hit this guy or this guy. But it's evaluated at 0. So unless it hits this guy, we get 0. So we get 1 by L g of 0. But g of 0 by definition is 1. Otherwise it wasn't regulated. So we get 1 by L. Okay? And so our LHS is equal to L lambda squared times some number which we don't know, but it depends on the cutoff, minus 1 by 12. Is this clear? What about other terms in the Euler Maclaurin series? Those proportional to triple element. Those all vanish. Because
you get the derivative
because
of g, it vanishes because of x, and if you take the
derivative of g, it brings out 1 over lambda. Okay? Any derivative acting on g brings out factors of 1 over lambda. We will be interested in the limit lambda goes to infinity. So those quantities in the continuum limit all are vanishing, so we can ignore them. So there's only one term that survives in the lambda goes to infinity limit that is of interest to us. And that term is unambiguous. It's completely determined. Its L dependence is determined, the number is determined. It's minus 1 by 12 there. If you look at how Polchinski does this derivation, chapter 1, he does more or less the same thing I'm doing, except that he uses a specific g function, some exponential. You can try it out with that function, just to make sure that I'm not fooling you. You can try it with any function you want to make. Choose your favorite function. If you can actually do the integral of good, you'll check that everything I'm saying is true. Okay? Now, this quantity is precisely the form that can be cancelled by a local counter term. And so we will choose our counter term to cancel it. Once again illustrating a feature of quantum field theory that is ubiquitous. That is, the term that you get with a given counter term, with a given regulation scheme, is not universal at all. The counter term is not universal. But, given a regulation scheme, you tune your counter term to get something physical. And then no other detail matters. Okay? So whatever G we choose, we tune the number, the A thing I call A, in a counter term to cancel this. After that we define our field. Take lambda at infinity, we're good to go. Okay? So once we've done that, this is thrown away because the counter term part cancels this part. Okay? And we are left with an unambiguous number, which is minus 1 by 12 L. L for us is 1. So it's minus 1 by 12. And so, we finally have the formula that m squared, the mass squared of a state with given quantum, the effective mass squared operator, is equal to, somebody will have to help me with all the factors. Oh, yeah, no, somebody will have to help. D minus 2 by, where was it? There was some alpha prime.
There were 2 by alpha prime.
D minus by 2 alpha prime?
Into 4 by alpha.
D minus 2 by 2 into 4 by alpha?
4 by alpha prime.
Oh, sorry. Let me just do this way. So, what do we get? We got 4 by alpha prime, and you're saying sum over n, alpha minus n, alpha n, plus d minus 2 minus, no, wait, into minus 1 by 2. Okay?
some, I think we got some number in LHS which was independent of L. Would that
This will happen in the supersymmetric theory, for instance.
would that be a problem for the theory?
No, it would be. You'd have to go further to see a problem if there was. Right. You see, if you were working on the superstring in the Ramon set, this will happen. If you don't know what that means, I'll explain it to you. Okay? But you see, there will be many things that need to work in this theory.
Okay.
You'll see it.
Okay.
Other questions or comments?
That's minus 1 over 12 times L.
That's it. No, N is this. This is the full answer.
The L is gone.
N is 1 byte. So we were 2 byte. Our whole formalism depended on being 2 byte. By the way, we could have kept L free in the whole formalism. We've got various factors of L here as well. Everything would have cancelled. We just fixed L to be 2 byte. Okay. So we get is equal to 4 by alpha prime. Alpha minus n, alpha n minus d by 2 by 24. Okay. Wonderful. Now, can I 6-7 moments? We'll try not to make this happen. We're almost there. So, excellent. We've got a lovely mass formula for this string. But there's a problem. There's minus. Negative mass squares are tachyons. So if we take the ground state of the oscillator, we get a tachyon. Negative mass squares are tachyons. Now, you will sometimes hear people telling you tachyons are particles that move faster than the speed of light. This is absolutely untrue. Okay? So nothing moves faster than the speed of light. You will often hear very distinguished people saying this at eminent gatherings. They're talking nonsense. Okay? Nothing moves faster than the speed of light. Okay? Tachyons represent instabilities. Okay? The mass square, suppose you've got a scalar field. Okay? In some potential that looks like this. The mass of the particle is the second derivative above its minimum. If you're expanding the scalar field around here, you will get a negative mass square, and that's a tachyon. But there is a theorem that tells you that del phi, the whole thing squared, plus v of phi, for arbitrary potential v, is causal. It doesn't matter where you expand it around, it remains causal. So in such a theory, even though it has quote-unquote tachyons, nothing moves faster than light. There's no violation of general, causality in such theories. Okay? Okay? But what it is an instability. So, what we're doing apparently in this bosonic string is obtaining the perturbative expansion about an unstable vacuum of some theory. Okay. Now, if we knew what the right potential was, and the potential did have a nice minimum, we could move to that point and try to get that. We don't understand string theory at that level. We're not even sure whether there is a right vacuum for the bosonic string. Though I've written a paper claiming that there might be. Okay. But the real excuse for such could be that the bosonic string is expansion of around an unstable vacuum of something nice. But we don't have very clear evidence for that's the case. So the real excuse for the next 12, 13 lectures of this course is that even though there is this instability, a lot of things we study will not depend on it. Physics will. But a lot of the formalism we study will not depend on it. And we are training ourselves to think in a way that will continue to be useful when we study the actual theory we're interested in, namely the superstring. Both studies will be, unfortunately, technical studies. Okay? All the technicalities of the bosonic string carry over to the superstring, but the reverse is not true. So it's a good pedagogical device to first understand the superstring well, and then understand the bosonic string well, and then the superstring, so that you can separate complications. Okay? So this is the strategy Polchinski follows in his books, and I will adopt it because because it's useful. Okay, so the downside of this strategy is that you go through 15 lectures on something that you've declared to be unphysical from the start. It can be a bit demotivating. Don't be demotivated, okay? You've got to be serious and strong people. Wait for lecture 16. Okay. So now with that apology, we will continue. Okay. The bosonic string has a tachyon, but let us live with that for a moment. Okay. The bosonic string has a tachyon. Let us live with that for a moment and continue to analyze our problem. So what I'm going to do as a little exercise is analyze the spectrum of this theory as a function of mass in the first few states. So the lightest state of the theory is m squared equal minus 4 by alpha prime. By the way, I got this number right. I remember the minus 4 by alpha prime. Okay. Okay, yeah. So m squared is minus 4 by alpha prime. We've got this nice m squared equals minus 4 by alpha prime, and that's the ground state. What about the next state? M squared is equal to what? Well,
it's minus 4 by alpha prime only for d is equal to 26.
Sorry. I'm sorry. Minus 4 by alpha prime into d minus 2 by 3. Thank you. Okay. Then, what do I get next? By the way, you see that this formula was for the right movers, but there was an exactly similar formula for the left movers. Since the LHS is the same, it tells you that whatever the sum is on the left moving side, it must also be the same sum on the right moving side. This is a constraint because the oscillators of left moving and right moving oscillators are independent. There was no logical reason why they had to have the same oscillator number. Just subtracting the two constraint equations gives you that condition. Okay? So you cannot consider arbitrary level on the left side and arbitrary other level on the right side. The levels have to be equal. Just for consistency. Okay? So whatever this guy evaluates here is called the level. Let's see other state. Let's call this the level. Okay. This is what it is, whatever this is. Other states at level 1. Yes, there are states at level 1. You take the oscillators with energy 1. There are the states which are alpha plus minus 1 on vacuum. The plus represents right movers. But because if you have level 1 on the right side, you must also have on the left side. You get alpha minus 1 nu acting on vacuum. Such states have level 1. Okay, sorry. This was I. We didn't have oscillators for plus and minus. We only have for I. No, we don't. I completely arbitrary. Okay? Now, what is the energy of this state? The mass squared is minus 4 by alpha prime into minus b minus 2 by 24 plus 1. Now we're going to ask, in what representation of the Lorentz group do they transform? How many? Well, what representation of? Let's classify. Okay, let's classify these things in representations of SOB minus 2. So what we got is a vector times a vector. Now you've got a vector times a vector. What can you make? You can take the trace, so that's a scalar. You can either symmetrize with trace removed, that's a symmetric tensor, or you can symmetrize with anti-symmetrize, trace is automatically removed there. That's an anti-symmetric. So what you get is vector times vector, which is equal to sim as and scalar. Oh, SOD minus 2. Is this clear? that might immediately be worrying you is, look, we're getting representations of SO B minus 2. Now this looks like it's in conflict with Lorentz invariance. Because though we set up a gauge in which only B minus 2 is, SO B minus 2 is manifest, we should have got a Lorentz invariant theory. Now in the Lorentz invariant theory, massive particles are classified by representations of SO B minus 1. This is the famous Wegener little group analysis. Okay? Anyone who doesn't know about this should read about it. Or come and ask me about it. So the little group analysis of Wegener tells you that particles, massive particles just because you can always make a Lorentz transformation to get the momentum to be 1, 0, 0. Massive particles are classified, species of massive particles are classified by representations of SO B minus 1. However, this is somewhat weakening. Species of massless particles are classified by representations of SO B minus 2. So this thing looks non-Lorentz invariant. Unless it so happens that these particles are massless. Okay? So this theory, even just classically, even ignoring even ignoring the technion, looks like somehow there's some inconsistency, because if you put a gauge that breaks a certain symmetry and get an answer that breaks that symmetry, you've done something wrong, because physics should be gauge based. Looks like our answer is inconsistent unless it so happens that this thing is massless. But this is massless provided D is equal to 26. Okay? So there's a hint here that something is going wrong unless D is equal to 26. But now, none of you is going to believe this hint, because you're going to say, well, okay, you got lucky at the first level. You got to promote SO 24 representations. I mean, you got to live with SO D minus 2 representations because you said the first level was massless, but your luck runs out at the next level. Because if one level is massless, then the next level is clearly massive. Well, everything is arranged in representations of SO D minus 2. So we've tried to be very clever, but what will you say at the next level? So let's try. Let's look at level 2. Okay? Now what are the states? Separately for left and right movers, we could have alpha minus 2 mu on 0. Everything gets squared again. I'm just counting either left movers. Or you could have alpha minus 1 mu, alpha minus 1 mu on 0. These are level, again I emphasize, I'm just writing down, let's say left movers. Everything is squared. We worry about the square. Now, sorry, not mu, everything's RJ. Sorry. I, J. Now, everything here looks like it's an SO24 representation. Okay? Yeah, so that's it. SOD minus 2 representations. Everything here looks like it's SOD minus 2 representations, unless what's actually going on is that this is the decomposition of a SOD D minus 1 representation into its representations under the sum group SOD minus 2. That's possible. Let's check whether that's working. Is there any SO D minus 1 representation whose decomposition into representations of SOD minus 2 is this object? Now, if you think about what is this? This is a symmetric tensor, but there's also a trace. So trace plus a symmetric. Why is symmetric? Because these guys are equal. Okay? Well, let's look at a symmetric tensor. It's just a d minus 1 times d minus. Sorry, it's a d minus 2 times d minus 2 symmetric matrix. Now, let me try to find some representation of SOD minus 1, which will decompose into these under SOD minus 2. Let me try the symmetric representation, symmetric tensor representation of SOD minus 1. So what is it? It's a d minus 1 times d minus 1 matrix. Okay? And let's say that the first guy, let's say, is the extra guy. So, how does it decompose? Well, here we've got a d minus 1 times d minus 2 times d minus 2 symmetric matrix. Okay? You could have the trace here as well. Here we've got, well, just a number, a singlet under SOD minus 2. And here what do we have? Vector. A vector under SOD minus 1. So, suppose we started with the representation that was symmetric for traces. That links this number to the trace of this. So removes this. So what have we got? We've got the following decomposition rule. That an SOD minus 1 symmetric tensor decomposes into an SOD minus 2 symmetric tensor, a vector, and a scalar. Well, that's exactly what we have. A vector, the symmetric tensor, and if you take the trace part, it's the scalar. So, in fact, the content that we got just for left movers is precisely right to be exactly an SOD minus 1 symmetric traceless tensor. A single SOD minus 1. Same on the right. Same for right movers. Now we've got two representations of SOD minus 1. You take the tensor product of them, you have to do some complicated Clash coordinating, but whatever you get will clearly be representations of SOD minus 1. So it worked. You know, the one trick that we played at level 1 was all we need. In fact, one can prove, and we will go through this using more sophisticated techniques in the course. One can prove that at every level, all the states that you get by this formalism can be grouped together into representations of SOD minus 1. Except at level 1, when it cannot. Okay? So, this whole spectrum actually represents a Lorentz invariant spectrum of the theory, provided D is equal to 26. Okay? So, we reached the provisional conclusion that we've obtained Lorentz invariant motion, a Lorentz invariant quantization of an unfortunately unstable theory. Okay? Provided D is equal to 26, but not if D is anything else. Right? Now, of course, this is not satisfactory. It's not satisfactory because you say, well, I mean, I don't like doing physics in this hit and miss way. If D was not equal to 26, clearly we must have done something wrong. Otherwise, why will we not get it? In our derivation, we didn't assume. And we will see this. We will see that actually the thing that we do wrong is that this while invariance that was so crucial for the logic of our procedure is at the quantum level. Classically, we see symmetry. At the quantum level, ceases to be a symmetry of our theory if D is not equal to 26. And that is what leads to trouble. Okay? But often if you have trouble, you spot it in many ways. Here, even without quite understanding what the trouble was, we saw that we have trouble unless D is equal to 26. Okay? So this hint that we're getting from Lorentz invariance is the correct hint. Okay? We've got a beautiful quantization of this bosonic string, unfortunately unstable, provided D is equal to 26. Okay? So this is the famous statement that all of you have heard, that string theory is inconsistent unless we live in Lorentz invariant string theory. It's inconsistent unless we live in particular dimensions. And you see where it comes from. It comes from, at the technical level, maintaining while invariance, which was a requirement because we got a tractable formalism of the theory, only relating to what we actually wanted, only if the theory was while invariant. Okay, this is beyond my control. So, okay, yes. So let me stop here. Unless there are, even though we're late, since this is all very important, if there are 2 or 3 questions or comments, let's take them. Okay, so we completed our first pass quantization of the string. Not bad, 3 lectures, right? Not bad. Okay, so we've completed our first pass quantization of the string. But this subject is very well understood. And we will go back now and do a much more thorough job using the techniques of what is called conformal field theory. that we will start next time. But many of the main ideas are already. Okay. So if you have questions or comments, please.
Everything goes through for open strings, is there or something?
Everything goes through for open strings. Yes, absolutely. Everything goes through for open strings. It'll be a bit easier to discuss that once we understand a little bit of topology theory. Okay, so I'll postpone that till we just because it's possible. Everything goes through for open strings. Yes, we'll discuss that a little bit. Yeah, see, this is a very good question. You see, the two things that you have to decouple. The first is the quantum field theory that lives on the world volume of the string. And the second is the space-time motion it describes. The quantum field theory on the world volume of the string has no instability. It's a bunch of harmonic oscillators plus zero mode motion. Perfectly fine, well-defined theory. However, once we did the quantization, you remember that there was an interpretation of the final constraint. That interpretation gave you a Klein-Gordon equation that told you were dealing with an unstable theory in space time. Okay? So what's going on here is that what we're doing is developing a set of Feynman rules. Okay? There's something I should have said that I didn't say. No, I'll say that. But developing a set of Feynman rules for the expansion of some theory. Okay? But what that theory is, we discovered. And we found that we developed a set of Feynman rules for the expansion around an unstable space. No problem with the world sheet theory of this. Okay? Now, there's one very important thing that I didn't say, that I'm going back to say, and I didn't pick up. You remember that we got massless spectrum when we looked at level 1. Remember what the content of that spectrum was. It was symmetric tensor, antisymmetric tensor, and scalar. Firstly, we've got a massless scalar. Sounds pretty weird, but okay. Then we've got an antisymmetric tensor in 26 dimensions. If you're not familiar with that, it also sounds pretty weird. But the thing that's really weird is symmetric tensor. Why is that weird? It's weird because it's not weird. Because you know of a famous theory whose linearized excitations are indeed symmetric tensor representation of its little group of SOD minus 2. And that's Einstein's theory of gravity. The linearized fluctuations of the graviton transform in the symmetric tensor representation of SOD minus 2. Now, there is also this folk theory that a number of people have, including Feynman, have worked on trying to make it a precise theorem, more or less, which is that it is impossible to make a consistent theory of a massless symmetric representation unless that theory has diffeomorphism invariance. The spirit behind the statement is simply that, you see, when you do the canonical quantization, you get some oscillators with the wrong sign. Because there are time variables, very much like Maxwell theory. Unitarity then, if you had physical states transforming that could be created by these oscillators, this would violate unitarity. In order to get consistent theories, you need some mechanism to kill those oscillators. Only mechanism we know of in physics to do such things is a gauge invariance. So Feynman and company start by evaluating the only linearized gauge invariance that could work, and then try to show that as you complete this order by order to non-linear orders, full diffeomorphisms arise. Okay? So, if you believe this folk theorem, one should always be suspicious of theory.
FOLK.
What? FOLK. If you believe this, it's not even a theorem in any sense. In general, in physics, you should be suspicious of theorems. Because theorems always come with assumptions. Okay? And the assumption may not be relevant to your physics. Okay? But you should always be doubly suspicious of folk theorems, because the assumptions may not be true and the proof may not be true. Nonetheless, this is widely believed. And if you believe it, then what must be true is that this string theory, whatever it's describing, perturbative expansion of some theory, but whatever that theory is, must be a theory of gravity. This says the current reason to be excited about string theory. Because, as most of you know, there have been many attempts, but in my opinion, none other even half successful attempts to produce a quantum theory of gravity. So already we've seen our first hint of something really nice, namely that gravity is emerging. And we will see this in much more detail. Okay, sorry, I'm through unless there are questions. Go on.
The plus minus indices for left, right, for these level 2 states, can you, it's not very clear about that.
Everything is either plus or minus. Okay, so what we get, so what have we got? We've got sim traceless from left times sim traceless from right. That's the full representation. Now symmetric traceless of SO d minus 1. Now you have to be a group theory champion to be able to do this decomposition. You know, it's subject to you have to really think about it. But for my purposes, I don't care. What I want to know is, were they representations of SOD minus 1? Now the tensor product of two SOD minus 1 representations can always be decomposed in SOD minus 1. So to actually enumerate, you have to think hard. We don't care. Okay, good question. Another question.
Individual sector can be calculated.
Yes, and that's how it always works. The reason it always works that way is, by the way, it's the open string. Because everything we had did here would go through for the open string with just one of these things. So for the open string to be Lorentz invariant, sector by sector. So it's never some tensor product you give the thing. It's always left and right over center. Good. Any other questions? Okay, thank you. Sorry for this.